had an info session, and there weren't many people there. We'll just run back this slideshow one more time, just so you guys know what's going to be happening in this class. By the way, can you guys hear me?
Yep.
Okay. So, hi, my name is Ryan. I'll be your main teacher for this class. And we also have three wonderful TAs who are going to help me facilitate class throughout these weeks. Personally, I am a rising senior at Woodbury High School. I've been doing math competitions since I was a middle schooler in math masters. I did math counts, AMC 8, 10, 12. I'm a four-time Amy qualifier. Yeah, I've also been a part of the All-State math team. So yeah, I've had a pretty thorough experience with math, and I like it a lot. So uh, it'll be a blast teaching you guys. TAs, if you guys want to go next and just briefly introduce yourselves.
Um, Hi, I'm Gotham. Can you hear me?
Yeah, we can hear you.
Okay. Hi, I'm Gotham. I'm gonna be the freshman next year, and I've been doing comp math since fourth grade or fifth grade through math masters. I've done math masters, math league, math counts, AMCA. Yeah. So I'm excited to be TAing for this class.
Manish is unfortunately not able to make it today, but he'll be here next week. So
And then Arush.
I think he might be having some technical difficulties.
Okay.
Uh, Hi. I'm Arush. I just finished eighth grade. Wait, can y'all hear me?
Yeah, we can hear you.
Yep.
So I just finished eighth grade. I'm going to Wayzata High School next year. And I have a lot of interest for math. I did UMTM, if any of you guys know that, and I also have a lot of interest for competition math. I did AMC 8, math counts, math masters, AMC 10. I qualified for Amy this year, and I did pretty good for the first year. So yeah, I'm excited to be a TA for this class as well.
All right, awesome. Okay, so just a brief summary of the AMC 8. It's called the American Mathematics Competition, is what it's short for. And it's a nationally recognized middle school math contest, which focuses more on problem-solving skills rather than memorizing formulas. And so, although we will be learning a lot of formulas in this class, we want to stress the ideas of mathematical creativity and problem solving rather than just memorizing formulas. And so the competition is open to students in 8th grade or below, and it consists of 25 multiple choice questions, which you'll have 40 minutes to answer. So you have a little bit over a minute to answer each question. Um, and the topics covered will be from algebra, geometry, counting, and also number theory. And we'll go over in a second what those topics mean. Another thing to consider is that on the AMC 8, there's no deductions for incorrect or blank responses. So if you really don't know what the answer is, it's in your best interest to just guess because a correct answer earns you 1 point. Incorrect or blank responses will just give you 0 points. And so the AMCA is really a starting point for math competitions into higher level math competitions like the AMC 10, AMC 12, AME, and also other national competitions like RMOL, HMMT, things like that. And so it's important to get those basics down as early as possible so that you have a better starting foot for later math competitions as well. And so the competition is typically held in February, where you can probably register with your school or find, I know UmpTyUmp has an official site for the AMCA, I'm pretty sure. So if you're in UmpTyUmp, that's a great place to take the AMCA as well. So our class schedule, starting today, we will meet for class every week from 6 to 8 p.m. And students can really come at any time that they want. They're not obliged to show up to all classes because we will post all recordings to YouTube and class materials to Google Drive and Google Classroom. So yeah, really just um, feel free to come or don't come. It's a pretty flexible schedule in terms of how often you want to show up. Okay, so this is the meat of the class. So it's split up by subject. So the first 3 weeks we'll go over algebra. Next 3 weeks, number theory, then geometry, combinatorics, and then we'll have sort of a bonus week to cover some more niche ideas like puzzles, graphs, and game theory. Um, so yeah, if you guys want to take a picture of this, you can. Um, I think we'll probably post this later as well for you guys to see too. Okay, so besides today, since we're going over this sort of outline again, we'll have 40 minutes of lecture to begin class, followed by a 5-minute break, probably more like 10 to 15, but we'll see how things go. And then our second part will be problem solving. So every week you'll get a worksheet to work on. That's where the majority of class time is going to be spent, is just you guys applying what you learned in lecture with the real AMCA problems. And during that time, you can ask myself or any of our TAs any questions you have with the problems, and we will be glad to ask. And then at the end, if you still have any unanswered questions, we'll have detailed solutions and some time set aside just to go over the worksheet. And then lastly, outside of class, homework. The homework is optional, but it's very strongly recommended. It's just going to be 3 problems, but those 3 problems are going to be very difficult in terms of what we learned in class. And so it's just good enrichment on top of what we do with the worksheet in class. And I would say probably only if you're comfortable with all the problems on the worksheet should you try to go and attempt the homework problems because they're meant to be pretty challenging and something that you want to spend some time thinking on. So yeah, that's sort of just what class will look like and also homework. So these are some real problems, just to get sort of an insight into what these competition problems look like when you compare them to, regular school math. And yeah, I think that's it for our introduction to this class. If you guys have any questions, feel free to ask in chat. Yeah, we'll probably just wait for a minute or so, see if you guys have any questions. Oh, how and when do I register? So usually, I think schools offer the AMCA competition. So try to reach out to your school and ask if they do have that. If your school doesn't offer the AMC 8, try asking around at other schools, because you're bound to find a school that will host it. Also, if you're an umpty-ump, yeah. Also, if you're an umpty-ump, that's another great way to register. And yeah, you want to probably register sometime in January because the competition is in February. Okay, then. Okay, can you guys see my whiteboard? Ooh, actually, yeah.
Yeah, we can see your whiteboard.
You see it? All right, perfect.
Yeah.
Okay, so this week we're just going to go over some basics in terms of algebra and arithmetic that the AMC 8 likes to test a lot. And so that mainly comes from these statistics. Um, so you've probably learned this before. It'll probably be a review, and that's okay. We will work towards some pretty difficult problems. So just sit tight and follow through. So the mean is the average of all terms in a list. And so what we mean by that is, say we have like 1, 1, 2, 3, 5, right? This is our list. And then the average is, well, we take all the terms in the list, we add them together. So 1 plus 1 plus 1 plus 2 is 4, 4, 3, 5. I think should be 12, right? And then we divide by the number of terms in our list. So 1, 2, 3, 4, 5. So we take 12, we divide by 5, and we arrive at 2.4 is our mean. Does that make sense? Okay. So next is the median. The median is the middle number in a set. So if we take the same set up here, right, the number in the middle is going to be 2, right? You have two numbers on this side, you have two numbers on that side, so it's going to be 2, right? It's very clear when there's an odd number of terms, right? Here we have 5 numbers. And so if we have an even number of terms, so say we had 1, 1, 2, 2, 3, 5 instead, right? There's no clear middle number because we have 2 and 2. And so what we have to do is we have to take the average of the middle two numbers. So in this case, 2 plus 2, right, is the sum, and we divide by 2 because there are two numbers. So the median is still 2 in this case. Okay, I don't see any questions. So next is the mode. So the mode is the most prevalent number in your list, the one that shows up the most. So for example, if we take this list up here, right? Well, all of these numbers show up once except for 1, right? 1 shows up twice, so 1 is our mode. And since we know 1 has to be the mode, this is also what we call a unique mode. For a list like this one down here, right? This one, well, 3 and 5 only appear once. 1 and 2, however, both appear twice. So there actually is not a mode. Well, you could say that 1 and 2 are both the mode, but in this case, this mode is not unique, right? It's not one number that stands out. And so that's just some vocabulary to keep in mind of is the AMCA will ask you to find a list or arrange something, and it'll say such that it has a unique mode. And so knowing that unique means only one of them has the most number of occurrences is important. Okay, so let's go over an example problem real quick. So this problem says if your average score on your first 6 math tests was 84, so first, oops, that's not how you spell first. Your average is 84. And then it tells you on your first 7 math tests, the average is 85. Then what was your score on the 7th test? So I'll give you guys just a few minutes to think about this problem. And if you have an answer, try to DM it to myself or a TA, just so it doesn't spoil it for anyone else. Oh yeah, Albert, go ahead.
Wait, I can say the answer?
Oh, try to just DM it, message
Yeah.
it to, yeah, a tutor.
Preferably DM it, and then we might ask to like we'll select someone and ask them to share how they got the answer.
Yeah. If you feel confident, we can definitely have you share how you solve this problem. Okay. Do we have anyone who wants to share their solution? All right, if not, that's okay too. I can just go over it real quick. So if we go back to the formula for mean, right? Mean means we take the sum of all the test scores and then we divide it by the number of test scores, right? So let's say S is our sum, right? Then we know here, right, that we're taking our sum, or let's just use S. We're taking S over 6, and that gives us an average of 84, right? So this means that if we move the 6 over, right, we have that S is equal to 84 times 6, and this comes out to be 504, right? And the idea here is we want to find what S is because we are also given that the first 7 math test scores is average 85. So we want to try to use these things together to find the 7th test score, right? And so another thing we should note is that this S here is the sum of the first 6. So we should probably say 6, right? S sub 6. And then if we look at S sub 7, right? The sum of the first 7 test scores. Oops. Well, now we have that S7, our sum, divided by 7. This is our average. We are given that it's just 85. Right? So now, if we multiply 7 over, right, we get that S7, oh, and this should say S6, is 85 times 7, which is equal to 595. And so the big thing to realize here is if we sort of consider each score, right? Let's say the first score was A1, and then the second score was A2, third was A3, and so on, right? Up until A7, right? The sum of the first 6 means we take A1 plus A2 plus A3 all the way up to A6. The sum of the first 7, A1 plus A2, right? All the way up to plus A6 plus A7. And we know that this is 504 and 595, right? Because we found it up here with the average formula. And so now, if we want to find what the seventh score was, all we have to do is just subtract this equation from this equation, right? Because subtracting these two will cancel out all of the other test scores and just leave us with A7. So A7 is equal to 595 minus 5. Oops, that's not 5. 504. And this gives us 91 as our final answer. Does this make sense? Okay. I don't see any questions, so we can move on. So let's go over another average problem. Okay, this one says, which of the following has the largest average? And so the five options it gives is multiples of 2 between 1 and 101. And then the next option is multiples of 3 between 101 and 4 and 5 and 6. So it's essentially asking um, which has the largest average among the sets of multiples of 2, 3s, 4, 5, and 6 between 1 and 101. So this first option, right, would go 2, 4, 6, 8, all the way to 100, right? And then for the set of multiples of 6, it'd be 6, 12, 18, all the way up to 96. And so the question is asking which of these sets has the largest average. So I'll give you guys a few minutes to think about that. Okay, in the interest of time, I'm going to cut this one short just a little bit. I don't think I received any correct answers, so I will just go over the solution. So the key thing to realize here is that this actually bleeds into our next topic. It was sort of a test of whether you already knew about arithmetic sequences. But really the idea is to notice that 2, 4, 6, 8, right, all the way up to 100 is that the average of these numbers is just going to be essentially it's going to be measured by the average of the largest and the smallest numbers. So what I mean by that is 100 plus 2 divided by 2, which gives 51, right? And then so for 3, it'd be 3 to 99, right? So that would also be 102 divided by 2 is 51. And then next we would have 4, 8, all the way to 100. So this would be 52 actually. And then the next would be 5, 10, also up to 100. So this would be 105 divided by 2, which is 52.5. And the last one is 6, 12, all the way up to 96. And this would be 102 again. So this would give 51. And so from here, we can see that our answer is the multiple of 5s. And so some intuition for how we sort of get this formula is if we think back to average, right? Average is the sort of common number across all the numbers, right? So if we have something like 5, 10, 15, 20, 25, right? All the way up to 100, right? So if we just look at the middle two numbers, I believe the middle two numbers are going to be 50 and then 55, right? And then on either sides, it's going to go to 5 and it's going to go to 100, right? So what you want to realize is that the average of all these numbers is just going to be the middle of these two. Essentially, what we're saying is, right, since everything is equally spaced, we're going to have like 45 on this side, and then over here, we're going to have 60, right? What you'll notice is that from here to here, right, we have two numbers that add up to 105. If we increase this side by 5, and we decrease this side by 5, well, then these two numbers are still going to have the same sum, right? And so across all of these pairs of numbers, what's going to happen is we are just going to be adding a bunch of 105s. And so in the end, our average is just going to be measured by these pairs, right? And so this idea is the same for every single one of these because every single one of these has a common difference, right? It's always up by a certain number, right? Up by 6. And then for like 4, right? This one goes up by 4. So this one follows the same pattern. So really, this is why we just add the first and the last term and we find the average. Technically, you don't even have to find the average because you're just dividing by 2 for all of them. It doesn't change which one is larger. But yeah, this is sort of a more applicative approach to looking at averages, right? It would take a while to add everything up and then divide it by a certain number. And so this is why these problem-solving abilities here matter a lot on the AMC 8 because this saves a lot more time. So yeah, something to keep in mind. Okay, so this is about it for mean median mode. So we're going to move on to our next topic for today, which is arithmetic and geometric sequences. Oh, I can see it's right around 6:40. Since we had that info session at the beginning today, we'll just bleed into the problem solving session a little bit, just so I can finish up lecture. So, arithmetic sequences and geometric sequences. Right? So there's a pretty good chance you guys have also heard of these before. And the idea still stands that we're going to learn some basics, but in the end, it's about problem solving with these ideas, and how you can gain information out of them. So starting with arithmetic, I think it's important to first list how we would sort of represent each one of these. So how I would go about representing an arithmetic sequence is it's just a list of numbers which has a common difference, right? So you start with like a number A, right? And then your next term would be A plus D, right? Where D is your common difference. Right? So then following this pattern, your next term would be A plus 2D, right? And then A plus 3D, and so on. And so, like I said before, right, as you can see, actually, this previous problem was about arithmetic sequences. And so a property we gained out of arithmetic sequences is that the average of an arithmetic sequence is just going to be the median, right? We showed it here with this sort of like a double pairing on either side. And if there's an odd number of terms, right, well, then we just know that the middle number is literally going to be the middle of the whole list. And so also what we need to know is how to represent the nth term. And so what I mean by that is like, say we have like the sequence 1, 4, 7, 10, 13, right? And this goes on forever. The way we represent this in a cohesive formula is, well, we want to look at the common difference, right? Our common difference here is always 3, right? So we start with 1, right? Because that's our first term. And then every time we go one more step, right, we add another 3. So we want to put a 3 here in front of some value of n, right, where n is the nth term. So let's say that this is the first, second, the third, right, the fourth, the fifth. And so our complete formula then would be 3 times n minus, or 1 plus 3 times n minus 1. So if we plugged in like 4, for example, here, right, this would give us the fourth term, right? So 1 plus 3 times 3 equals 10. We can come up here and check, and it indeed does give us 10. And so the reason why we have an n minus 1 here instead of just an n is that we start with the first term by itself. And so that means we don't want to add any 3's to it yet, right? We start with 1 up here. So instead of, since we start with 1, right, we want to subtract 1 because we don't want that 3 yet. That 3 will start on the next term. And so that's why we have this n minus 1 instead of n, because n would sort of just shift everything up one more place.
Could I add something?
Yeah, sure.
You could also, if Like you could subtract so you get the zeroth term as -2. So you're already taking you could also do 3n minus 2, and I'm pretty sure that would also work for the formula because then you're taking the zeroth term, right?
Right, yeah, exactly. So we could also expand this um and get something like this. And in the same way, you can derive it if you found like, the zeroth term or the -1th term, something, oops, not -6, -5, right? Something like this. And either way, it would work all the same, as long as you remember sort of what term you're trying to start on, and not shifting things. It just depends on how you label this. So if this was labeled as 0 instead, right, we would have to shift everything by 1. And so usually it doesn't matter how you label these things. What matters is that you keep track of which part is labeled in a certain way to make sure that you get the right number and you don't have like a one-off error. Okay, so aside from just the basic formula, right, we also have the sum of the terms. So going back to this problem again, right, we found that, right, if we have an arithmetic sequence, since it goes up by the same number each time, we have this sort of like rainbow that can go across all of the terms. And this rainbow just suggests that if we pair the right numbers up, we can get the same number over and over again, right? And that's a lot easier than adding each one up individually. So using this sort of rainbow technique, what we can say is, hey, we just take the first and the last term and we add them together, right? Because it's going to be the same across all of these pairs. And then what we do is we multiply that number by the number of terms, and then we divide by 2, right? We divide by 2 because, well, we want the average of these two and not just the sum. And so what this formula looks like, right? So yeah, let's use this just for a general formula, right? So let's say this ends at like a plus n times d, right? And then our formula is going to be the first term, right? A plus the last term, a plus n times d. And then we want to multiply that by the number of terms, right? So sometimes this is tricky. Just make sure you're counting right. So we start with 0d and then 1d, 2d, 3d, all the way up to nd. So we have a total of n plus 1 terms. And then in the end, we want to divide all of this by 2. And so this is the general formula for um, an arithmetic sequence sum. So if we go back to our example, right, let's say 1, 4, 7, 10, right? Let's say we want to find the 100th term in this sequence, right? So let's use our formula we made up here, right? 3n minus 2. If we want to find the 100th term, we just substitute in 100. So 3 times 100, right, minus 2. This will give us 298. So this is our 100th term. And then say now we wanted to sum all of these numbers up. Well, now we have to use the formula, right? The formula is we're going to take the first term and add it to the last term. And then we're going to multiply it by the number of terms. So here, the number of terms we know is 100, right? Because we just said the 100th term. So 1, 2, 3, 4, blah, 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 100. And then in the end, we divide this by 2. So this will give you 299 times 50. I don't know what the number is off the top of my head, but I'm sure it's not too hard to calculate. I think it's like 14950 or something like that. Okay, and that's about as much as you need to know for arithmetic series. and sequences. And so next what we have are geometric, right? So geometric here, instead of adding, we have multiplication, right? So we start with our first term, let's call it G, right? And then you have a common ratio. So our next term is going to be G times R, and then it'll be G times R squared, and then G times R cubed, etc. All the way to like G times R to the N, right? And so similar to this one, the general formula for this, so let's say we have like 1, 3, 9, 27, 81, right? So basically just powers of 3. The first term is going to be 1, right? So we start with the 1, and then we're going to multiply it by a certain number of the common ratio. What is the common ratio? Well, it's just 3, right? We're just multiplying by 3 every single time. So we want a certain power of 3. And then now here, once again, we have to be careful, right? So if this is our first term, we don't want to multiply it by any powers of 3. So 0. So we want to start the nth term, which is 1, with 0. So we want to take 1 and subtract 1 from it so that when we plug in 1 to this, right, we'll get 1 times 3 to the 0. And that's just going to be equal to 1. So this is our general formula for this geometric sequence here. And then so similar to the arithmetic sequence, there is a formula for a geometric sequence sum, right? So say we wanted to take like 1, 3, 9, 27, 81, right? So you just wanted these, right? So it'd be pretty easy to just say like, oh, okay, this is 10, and then like these two are 30, this is going to make 40, and this is 121, right? But what happens when it asks like all the way up to the 100th term? So that would be 3 to the 99. And so here, the formula we're going to use is 1 minus R to the N over 1 minus R. And so what this means is wait, is this correct? I think it is. And then we just have to account for G, I'm pretty sure. I'm pretty sure we just multiply this by G. And you'll see in a second how we derive it. So if I get it wrong here, I'll just correct it anyways. So the idea with finding the sum is, so let's start with this G example, right? G, and then we have G times R, and we want to add these together, right? GR squared. We go all the way up to G times R to the N, right? The idea is if we call this value like V, for example, right? What we can do is we'll take V and we will multiply it by G. What this does is we get, or not G, sorry. We multiply it by R. What this does is we get GR plus GR squared plus all the way up to GR to the N plus 1. And what we see here, right, is that this part is all going to be the same. So what we want to do is we want to subtract them. So subtracting them is going to give us V times R minus 1, right? This minus that equals GR to the N plus 1 minus G. And so our V is going to be equal to G times R to the N plus 1 minus 1 over R minus 1. So this is just a little bit different from what I said up here. This is if you're going up to a different index. I mean, really, it's all the same formula. And also, this is swapped around by just like a negative sign, which is also the same as what we have down here. And so the key idea is not to memorize this formula, but to remember how we come up with it, right? Because if you can just come up with this formula every single time, it's a lot easier than memorizing, and it doesn't take a lot of time to come up with it. So like here, if we take our example with 3 to the 99, right? Then our sum would be using this formula, it'd be 3 to the 100 minus 1 over 3 minus 1. And so I can't simplify that, unfortunately. But this is useful to have in case we want to do any more work on a number like this, because it's a lot easier to work with uh, a concrete number rather than just like a giant list of numbers.
And then you multiply that by G, right?
Yeah. Oops. Well, and so G here is just one. That's why I kind of disregarded it. But yes, that's right. That's important. If it started with something like 2, right, then all of a sudden all of your numbers are multiplied by a factor of 2. And then you would have to multiply this by 2 at the front. So yeah. Okay, and so next up, what I want to talk about is we've talked about adding together terms in an arithmetic and geometric sequence. And so just some formulas that are good to know are other sequences. So say we want like 1 squared plus 2 squared plus 3 squared plus 4 squared, or like 1 plus 2 plus 3 plus 4 plus all the way up to n, right? And then here it'd be n squared. These sums are really good to know just in case you have to do something like this. And so we can actually do this first one here because this is just an arithmetic sequence, right? So what we do is we take the first one plus the last one. So we have 1 plus n. We multiply by the number of numbers, right? And it goes up to n. So there's n numbers. And then we divide by 2. And so this is the general formula if you're just adding from 1 to a certain number. For this next one, it's a little bit more complicated. Since we're running out of time, I'm not going to show the derivation, but it's good to know that this is n times n plus 1 times 2n plus 1 all over 6. And then the last one is 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. And it turns out this one is actually just the square of this sequence up here. So it comes out to be n times n plus 1 over 2 squared. So yeah, these formulas are also really important to know, and we will talk more about algebraic formulas either next week or week 3. I'm not sure, but we will go over more useful ones. These are sort of basic ones where you're, adding up a series or sequence of numbers. And then just the last thing I wanted to touch up on is the Fibonacci sequence. So this one is pretty important to know because sometimes they'll just ask random questions about it, or they'll have you like sort of prove a property in order to solve a problem. And so I think it's a good idea to just know what it is. Um, I mean, generally, I think it starts with 0 and then 1 and then 1, 2, 3, 5, 8. In the end, it doesn't really matter. You can start however you want, but I think these are the two most acceptable. And essentially, what the Fibonacci sequence is we just take 1 and then 1, and then we add these two numbers together to make 2. And then to make the next number, we just take these two numbers to make 3, and then these two numbers to make 5, and then these two numbers to make 8. And so this is what we call recursion, where you make a list from values previously iterated in the list. So yeah, I just wanted to bring up this because it has some pretty interesting properties. And I think it's also one of the homework problems. So I just wanted to bring this up in case we uh, come up with this in the future, just so you guys are familiar with what this is. Okay, yeah. I think that's pretty much it for lecture. Molly asked, what is recursion? Recursion is just like taking two numbers or taking a certain amount of numbers previously in the sequence to make a new number, right? So Fibonacci is one and then one, right? How do we make the next term? Well, we add the previous two terms to make two. We make the next number by adding the previous two terms, which is one and two, and then two and three, and then three and five. And so you could do something like say instead of adding, we're multiplying them, right? We could start with one and two, and then it's like, okay, what is the next number? Well, one times two would be two. Two times two would be four. Two times four is eight. Four times eight is 32, you know? Something like this is also what we call recursion. Um, and interestingly enough, this shows up a lot in counting. And so it's a bit of a more advanced topic for counting, but it's still good to know. And yeah, it's still useful for the AMC 8. I'm pretty sure there's going to be at least one or two problems that references recursion at least. And it's probably going to be in counting, but since it's a sequence and it fits with arithmetic and geometric sequences, we'll just talk about it today so that you guys know about it and are familiar with it. Is the process called recursion? Yes, the process is called recursion. So like this idea of like doing one thing over and over again to make new terms is called recursion. Yeah. Can it be with any starting number or just one or zero? The Fibonacci sequence is defined as one of these two. It must start with 0, 1 or 1, 1. That is just how it is. So if it started with like 3, 4, and then like 7, 11, this is not the Fibonacci sequence. The Fibonacci specifically refers to these two sequences. I guess if you did something like you like added another zero at the front, technically that would still be Fibonacci, right? Because like I mean it goes in the same place. But anything that differs by like multiple terms is not the Fibonacci. Okay, so since lecture is done, let's have a 10-minute break before we start the problem solving session. So grab a snack, drink some water, and we'll be back soon. Oh, why does a Fibonacci sequence seem so basic and complicated at the same time? Yes, that's true. I mean, it's a really simple principle that we follow in making this, but it also has some very complicated implications in terms of mathematics. And so, yeah, it's really simple, but at the same time, it also has a lot of meat to it, and it's really important in mathematics. You will see it a lot if you go further in mathematics. Okay, it's right around 7:50, so I'll be going over any problems you guys want to see the solution for on the worksheet. Are there any requests for any problems? Okay, great. Number 6. Um, actually, let's see what number 6 says. Oh, in January 1980, recorded 338 parts per million. The average CO2 reading has increased by about 1.515 each year. Okay, so essentially we start with 338 parts per millimeter, or parts per millimeter? No, parts per million. Yeah, I thought that sounded wrong. Parts per million, right? And essentially this just measures CO2. And the crux of this problem is that every year it goes up by 1.515 ppm, right? And I believe it asks from 1980 to 2030. Yeah. So if it goes up by this much every year, then essentially what we're doing is we're doing 338 and we're adding 50 years worth of 1.515, right? Because every year we're adding this 1.515 parts per million. And so this should be 75.75. So we add this to 338. And then we get 413.75. The question asks to round to the nearest integer. So our final answer should be 414 parts per million. Does that make sense? Yeah, I can post an answer sheet once class is over uh to Google Classroom for you guys. So yeah, we have the answers. So can we go over 9? Okay. What is 9? Oh, this one. Okay, yeah, this one requires some heavy algebra. So it says we have a sequence of numbers where the next number is the product of the previous two. So this is essentially just Fibonacci sequence, but we're multiplying. So it goes like 1, or like it starts with like 2, 5, and then like 10, 50, right? Because you're multiplying 5 times 10 to make 50, 10 times 5, and then 100 or 500, sorry. And then we do it again, we get 25,000. However, it says that this number, this 6th term in this sequence, is 4,000. And it asks what the first term of the sequence is, right? So what we have to notice here, right, is that if we just guess numbers, it'll be pretty hard to guess, right? So what we should try to do is write this in terms of variables, right? We should use algebra. So let's just say we start with the two numbers A and B, right? So if we start with A and B, right, then our next number is going to be the product of those two, A times B, right? And then after that, right, our fourth number is going to be this quantity times this quantity. So AB times B, well, that's going to be AB squared. We can do this again, right? Then our fifth number, sorry, is going to be A squared B to the third. We do this one more time, right? We take the product of these and we get A to the third, B to the fifth. So now in this sequence, we know that a to the third times b to the fifth has to be equal to 4,000. And so here, what we want to consider is, have you guys learned prime factorization? Because this problem relies on that a little bit. Oh, you guys know about okay, so essentially now what we want to do is we want to see because a and b are positive integers. So we know that they have to be factors of 4,000. So we're just going to test numbers that are factors of 4,000, right? Um, and so the way we want to do that though is more strategic, right? 4,000 we know is 4 times 1,000, right? So this is going to be 2 squared times 10 to the third. If you expand this further, it's going to be 2 squared times 2 to the third times 5 to the third. And so actually what we get is 2 to the fifth times 5 to the third. And would you look at that? It matches perfectly with what we have over here. So we know that B has to be equal to 2 and A has to be equal to 5. So that means our first term of the sequence must be 5. Does this make sense? I know this sort of covers something that we haven't gone over yet, which is prime factorization. But I think you guys understand how I got here, right? Yeah, makes sense. All right, great. Yeah, perfect. Okay then. So I guess what to take out of this is like the AMC 8 will do a lot to
Ryan,
try to Yeah.
I think someone want to do 7.
Oh yeah, I see that now. Thank you for letting me know.
Yeah.
Yeah, 7 covers infinite geometric sequences, which we didn't learn in class, I think.
Yeah, so I didn't explicitly go over it because I wanted to see how you guys would think about this problem like as a first time sort of thing. So obviously the idea is we start with $20 on the first day and then 10 and then 5 and then 5 halves, etc., right? And so essentially the idea is we can't really well, we can um, go about this the same way that we did in the lecture up here, if I can scroll to it. Sort of like this, right? And so the idea here is if we just call this like V, right? The common ratio is 1/2, so we're gonna have 1/2 V, and then this is gonna give us 10 plus 5 plus 5 halves plus all the way down. And so now what you'll notice is that now we don't have the problem of like one more number here that we have to subtract from 20, right? It turns out that everything here all just cancels out. Everything. So what we're left with is we just have to do 1/2 V equals 20. And so here V will equal 40. And so 40 is our final answer. So yeah, we didn't go over this in class because I wanted you guys to think about how you would apply this to a scenario like this. Um, and so I guess I can teach you guys right now. So if we go back, right? Well, where's the formula? Yeah, this is the formula we figured out, right? And so the way we modify this is, well, if n if n is getting really, really big, right? Let's say like 100,000. Then what we can say is if R is a ratio which is less than 1 and greater than -1, not equal to, then we know that R to the 10,000th or 100,000th power, right, to some really big number, this is just going to go to zero, right? So like if R was equal to 1/5, 1/5 to the 100,000th power is very, very small. And so it's just going to go to zero, right? In the end, we're actually taking n to what we call infinity. Infinity is, well, it's forever. It's can't be described using a number. And so essentially 1/5 to infinity is just going to give us zero. So this is more of an approximation. This is absolute, it's just going to go to zero. And so how we change our formula is we just do g times 1 over 1 minus r. And so this is also good to know. Does that make sense? Also, something really important to point out is this only works, this only works if r is between 1 and -1, right? Because r has to be a fraction that's less than 1 or greater than -1, because otherwise, like if it's 2, right? Obviously, it's not going to go to 0. It's going to get larger and larger and larger. Okay, then. Well, since it's 8 o'clock and we don't have any more requests, I think that's it for today. And so, actually, just one more thing. Do you guys want to play games during the break? Because I could like host like bomb party or something if you guys are interested.
Yeah, we can do that.
Oh, Albert? Oh, was that an accident? Okay, that's all good. Well,
You
um,
said you said that 1/5 to the infinity's power is go to zero will go to zero. Wouldn't that be like really, really, really close to zero?
well, since it's infinity, infinity goes on forever. So, I
It,
mean, it's not mathematically rigorous to say that this is equal to zero, right? Because like infinity is not a number. So that's why I use this sort of arrow to symbolize that it goes to zero. In the end, it becomes small, and we just say it's zero because um it essentially is. Yeah, for the sake of math competitions, it's okay not to be rigorous and to just sort of go with the formula. So if you see an infinite geometric sequence, you can sort of just say that this term will go to zero. You can just assume that it's, equal to zero in a way. Does that make sense?
yes.
Yeah, class ends at 8. So, if you feel like you want to leave, feel free to do so. I'm just wrapping up answering questions. So, yeah. Otherwise, I will see you guys next week.
Thank you. Bye.
Yeah, bye-bye.